Hi, my name is Justine Harkness, and in this video, we'll look at how to calculate the amount of energy stored on a capacitor. Just like batteries are sources of energy, capacitors also store energy as electric potential energy. And let's take a look at a capacitor. This capacitor is charged, it has its own particular voltage, and we're going to move these charges through a circuit. Now, on first glance, we might think, well, hey, if we move all of these charges through our voltage, our equation for electric potential energy is our voltage times our charge. However, if we look at our equation for the energy stored in a capacitor, we see that we have this 1/2. So let's think about where that 1/2 comes from. So we're going to start by moving our first charge through our circuit. Note that technically it is electrons that are moving, but since current is defined by convention as the movement of positive charge, here we are showing the positive charges in motion. But notice now we have less charge on our capacitor. The capacitance is equal to Q over V. So our voltage would be equal to Q over our capacitance. Since capacitance is constant, this means that if we have less charge on our capacitor, we also have a smaller voltage. So since we had 4 charges originally and we only have 3 left, we now only have 3/4 of that original voltage. And we're going to move our next charge through that 3/4 of a voltage. Now notice we have even less charge on those 2 plates. So our new voltage would be half of what it was originally. We move 1 more charge through. Notice now we only have 1/4 of our original charge, so our voltage is 1/4 of what it was originally. And finally, when we move our last charge, we're down to a voltage of 0. We've completely discharged our capacitor. So because the voltage is changing as our capacitor is discharging, each charge is moving through a progressively smaller voltage. And if we were to add up the energy of each charge as it moves through that voltage, what we'll get is 1/2 QV, where U is our electric potential energy stored on our capacitor, measured in joules. We have Q, which is our charge stored on our capacitor, and V would be the voltage measured in volts. That same potential energy equation can be written as U equals 1/2 CV squared. So let's think about where this equation came from. Coming back to our formula for capacitance, we know that C is equal to Q over V. And if we solve for Q, we get Q is equal to CV. And this is what we plug in for Q in that original equation, that U equals 1/2 QV. When we plug in Q equals CV into Q, that's what gives us this equation here. Now, one way we can increase the ability of a capacitor to store energy is to insert a dielectric between the plates of the capacitor. Dielectrics are covered in earlier videos on capacitors, but let's just look at how this works in terms of this equation. Our capacitance equation, C is equal to E naught ER, area over distance. The dielectric constant is that E sub R. If we have a capacitor that lacks any dielectric, the dielectric constant that we use is equal to 1, which is the dielectric constant of a vacuum and also the approximate dielectric constant of air. But if we were to insert a dielectric that has, say, a dielectric constant of 2, This would give us double the dielectric constant, which would double the capacitance. And coming back to our equation up top, if we were to double the capacitance, that would also double the amount of energy that we can store on that capacitor. So let's apply this with some practice questions. So this question tells us that we have a capacitor that has a capacitance of 100 microfarads and a voltage of 100 volts and asks us a few questions. The first question is, how much potential energy can we store? Now we have two different equations for the electric potential energy we can store on a capacitor. We have 1/2 QV, and we also have 1/2 CV squared. So we need to consider what variables we are given to determine which of these two formulas we need to use. So we are given 100 microfarads, our capacitance, and our voltage of 100 volts. So we want to pick an equation that has both capacitance and voltage, and that would be this second equation. So we're going to take 1/2 CV squared and plug in the values that we know. Now our capacitance was given in microfarads. We have to convert that by a unit conversion into farads. There are 1 × 10⁶ microfarads in a farad. So 100 microfarads would be 1 × 10⁻⁴ farads. And our voltage would be 100 volts. And remember, we need to square it. So if we crunch the numbers here, we'd find that we can store 0.5 joules of energy. Part B asks, how would this value change if a dielectric with a constant of 5 was inserted between our two plates? Now here we need to come back to our capacitance equation. The capacitance of a capacitor is our constant times the dielectric constant times the area over the distance. If we started out without any dielectrics, and we can assume so since we are inserting one, we started with a dielectric constant of 1, and we are inserting something that has a dielectric of 5. That means that we are increasing our dielectric constant by a multiple of 5, which means that we're going to increase our capacitance also by a factor of 5. Our electric potential energy is directly proportional to our capacitance. And say U is proportional to C based on this second equation. So if we have 5 times the capacitance, that means that we can store 5 times the amount of potential energy. So if we wanted to calculate out how much energy we would store, would be our original energy, or 0.5 joules, times 5, which would be 2.5 joules. How would this value change if the voltage was doubled? So let's come back to our equation. 1/2 CV squared is equal to our potential energy. Now here we are doubling the voltage, and our potential energy is proportional to the square of the voltage. So if we double the voltage, that means that our amount of energy that we can store would increase by a factor of 4. So if we want to calculate the new amount of energy that we can store, well, we started out with 0.5 joules. We can store 4 times the amount. So we would now be able to store 2 joules of electric potential energy. So now you should be able to calculate the amount of electric potential energy stored on a capacitor.